So take the second derivative. So remember, if I take the second derivative of the function ln x, well, that would be the derivative of the derivative, right? So derivative of, what's the derivative of ln x? 1 over x. And what is that equal to? What is that function, x to the negative 1? X to the negative 1, apply the power rule, you get negative 1 times x to the negative 1, which is negative 2. So negative x to the negative 2, which is negative 1 over, you agree? The derivative of 1 over x squared, 1 over x is negative 1 over x squared. And is it positive or negative? Does it matter what x is? It will always be negative. It doesn't matter what x is, right? So this is negative. And in particular for any x larger than 0, right? It is actually negative even if x is negative, but we don't care for negative values of x because the domain of ln of x is only the positive part of the real line, right? So we see that then if that second derivative is negative, that implies that the function is, so ln of x is concave down on its entire domain 0 to infinity. Everybody agrees with that? Now in WebAssign you should always write parentheses around x, okay? Otherwise you might get an error. In WebAssign, when you are writing ln of something, always use parentheses. Okay, so now we know that the ln function was increasing. Now we know it's concave down everywhere. Okay, if I want to sketch the graph of ln, what else do I need to know? Do I need to know anything else, or I can sketch it? What else do I need to know? What's that? ln x, and we know that its domain is 0 to infinity, right? We know that it is increasing on the entire domain. We know it is concave down on the entire domain. What else do I need to know to come up with the graph? Was that? Not necessarily. Well, we need to know the terminal behavior of this function. 3. I need to know the terminal behavior of this function. Those of you who didn't take Calc 1 with me, you might not have used that word, terminal behavior. What do I mean by terminal behavior? Anyone remembers? What do I mean by terminal behavior? I'm sorry? Yeah, how does the function behave at the extremes, right? Meaning that as x goes to infinity, right? If you look at the domain has two extreme parts, right? At infinity and what's happening at 0. So we want to know as x goes to infinity, what is happening to the value of log x? Is it going to infinity? Is it approaching a number? And what happens as x goes to 0 from the right side, because it doesn't make sense to ask what happens to the limit of ln as x goes to 0 from the left, because it's undefined there, right? So we need to know what's the limit as x goes to 0 from the right of ln of x. What is that quantity? And we also want to know what's the limit as x goes to 0 from the, not 0, x goes to infinity of ln of x. Okay? All right, so what I'm going to do is answer number 4 first, okay? Answer number 4. So notice, first of all, let me ask you this. What is ln of 2 to the n? Ln of 2 to the n is, by law number 3, is n times ln of 2. Very good. And is this positive or negative? Is ln of 2 positive or negative? What is ln of 1? Ln of 1 is 0. Now, because I know that the function is increasing, ln of 2 would be bigger than 0, right? Ln of 1 is 0, but the function is increasing, so ln of 2 must be bigger than 0. So I know that this is bigger than 0. Now, what happens to this as n goes to infinity? So let me ask you this. As n goes to infinity, what is happening to ln of 2 to the n? Ln of 2 to the n is going where? Ln of 2 to the n, is it going to a number? Is it going to infinity, negative infinity? What's that? Infinity, right? Because I have n times ln of 2, right? Ln of 2 to the n is n times ln of 2. So if n times ln of 2 is positive, then as n gets bigger and bigger, n times ln of 2 is getting bigger and bigger, right? So the limit of 2 to the n as n goes to infinity is infinity, right? What does it imply about the limit of log x? So does it say anything about the limit of log x? What's the limit as x goes to infinity of ln x? Does it say anything about that? Think about that. Think about this. We are saying ln of 2, ln of 4, ln of 8, ln of 16, ln of 32, right? So ln of these numbers is becoming bigger and bigger and bigger, right? But I know that the function is increasing, right? So that would imply that as x goes to infinity, ln of x gotta go to infinity as well, right? You agree? So we know number 4. So let's write down number 4. Number 4 is the limit of ln of x as x goes to infinity is infinity. So this I can say since ln of x is increasing on the domain. Okay. Now I need to know what's the limit at 0, right? What's the limit? What's the limit as x goes to 0 from the right side of ln of x? And here I'm going to do the following trick. Instead of looking at ln of x, I am going to look at ln of 1 over x, and then I'm going to take x goes to infinity. Let's see if you agree that they are the same limits. Notice that as x goes to infinity, 1 over x is going to 0. So I'm actually still taking log of something going to 0, right? So these two limits are the same. As x goes to infinity, 1 over x goes to 0. So I am still looking at what is log of a quantity that goes to 0, right? And so they are the same. Now, let's apply log rule number 2. What will that say? It will say that ln of 1 over x is what? ln 1 minus ln x, right? That's log rule number 2. What is ln of 1? 0, so I get the limit as x goes to infinity of negative ln x. Well, but this is the same as negative of the limit of ln of x. But what is the limit of ln of x? As x goes to infinity, we just showed that it is infinity, so I get negative infinity. Okay. So my limit number 3 is negative infinity. Okay. So I know that this information would be negative infinity. So I know exactly how the log behaves near 0 and at infinity. Near 0, it is blowing down to negative infinity. Near infinity, it blows up to infinity, right? Okay, so let's now draw the graph. Let me give you 30 seconds to try and draw it yourself from the four facts that we have. What are the 4 facts? Increasing, concave down, negative infinity at 0, positive infinity at infinity. So sketch the graph. See if you can come up with that. Remember, log of 1 is 0, right? So what's the x-intercept? X-intercept would be at 1. This would be x, this would be y, and y would be ln of x. Okay, so I think 30 seconds is probably up. Let's 10 more seconds, okay? Alright, so here is 1, let's say, and at 1 we get the point 1, 0, so this is 1. What's happening at 0? So here is 0. We know that as x gets closer and closer to 0 from the right, the function blows down to negative infinity. So I know that here it's at negative infinity. It means I have a vertical asymptote at which is y-axis, right? So I know that it is like this. Okay, and what is happening after 1? As x gets bigger and bigger, as x goes to infinity, the log function also goes to infinity, right? So it goes to infinity like this. Okay, so that's how it's increasing, concave down, everything is correct. Everybody's okay? All right. Now, one thing that I want you to realize here is that I am going to define a number here. Notice that because ln of x is going to infinity, what can you say about the range of ln? Range of ln. What is that? Yeah, negative infinity to infinity. So is one of the range values 1? Is 1 one of the range values? Okay. Then that means 1 must be coming out of some value of x, right? 1 must be coming out of some value of x, right? So there is a value of x for which log x is 1, right? We are going to call that number e. So what's the definition of e? Definition, e is such that ln e is 1. Okay? If you have seen the number e before, forget about it, okay? Just say that this is how we define the number e. The number E is the number for which ln of E is 1. Okay? And I'm going to tell you later how to approximate this number E. Okay? That's going to come up later. All right, so that's the number E. And okay, so those are the facts. Let's see what else. Well, let's do some examples now. By the way, you guys remember that your exam is coming up? If you look at the syllabus, the first exam time is what? The 13th, right? This is this Friday, right? I'm going to send you an email. I'm going to send you an email with what sections will be covered in the exam sometime today. Okay? But there is a new homework that has been posted on section 6.2 star. And I believe that is due on Thursday. Okay? All right, so what I want to do now is go over several examples similar to your homework problems. The first thing that I want to do is look at the following. You know what? Actually, yeah. Let me look at the following example. What's the derivative with respect to x of ln of x plus 1 over root of x minus 2. Okay? Okay, how would you find this derivative? I should be writing this, right? I should be writing parentheses around that quantity. But like I said again, I probably wouldn't write it all the time. What's the derivative? How would you evaluate it? So you're going to apply the chain rule first and then apply the quotient rule, right? Is that what you're saying? Say it again. Yeah, but I mean, it's not that bad. You could do it. But what I'm going to do is, before I take the derivative, I'm going to rewrite the function by applying the log rules. So that is, let's rewrite the function as ln of x plus 1 minus ln of root of x minus 2. So that's by using log rule number 2. And then I can still rewrite the second term. I can rewrite the second term. What is the second term? It is ln of x minus 2 to the what? 1/2. So that exponent half can be brought up at the beginning of ln. So this is going to be half ln of x minus 2, and this is by log rule number 3. You guys agree with that? Now I'm going to take the derivative. What's the derivative of the first term? I have log of x plus 1. If x plus 1 were just x, then we know that the derivative is what? 1 over x, right? But x plus 1 is not just x, but it is x plus 1 multiplied by the derivative of that, which is just 1 in this case, minus half. What's the derivative of ln of x minus 2? It is 1 over x minus 2 times 1, and then I can simplify it a little bit. Okay? Is everybody okay with that? Yeah. You see, if I had, for example, let's say I had 2x plus 1, right? If I had 2x plus 1, then I would be multiplying by 2 here, right? So what I'm emphasizing here, I am using the chain rule, but it turns out that the derivative of the inside is just 1. Is that okay? All right, now let's look at another example. This time, let's say y is x plus 1 over root of x minus 2. And the question is, find the derivative of y. Well, as it is, this problem does not involve the log, right? This is a Calc 1 problem. How would you find the derivative? Quotient rule, right? Is that right? You're going to apply the quotient rule? But I don't want to do it by using the quotient rule. I'm going to show you a different method for finding this derivative. And the method that I'm going to apply now doesn't really save you much work in this problem, but I'm going to show you another example where you'll see that this method makes things a little bit better. Okay, so this is known as log differentiation. Okay, log difference. I should say logarithm. Logarithmic differentiation. Okay, so the idea is that take the log of both sides. So you have ln of y would be the same as ln of x plus 1 over root of x minus 2. And then you're going to apply the log rules to rewrite the right-hand side. To rewrite the right-hand side, you're going to get, we have already done it, right? So I'm just going to do the following. This is ln of x plus 1 minus half ln of root of x minus 2, right? So you're going to rewrite it by using the log rules. And now, oh yes, thank you. It'll be x minus 2. Now we are going to take the derivative of both sides with respect to x. Now let me do the harder side. The derivative of ln of x plus 1, we saw that it was x plus 1 minus the derivative here would be 1 over 2 times x minus 2, right? You agree? Now what's the derivative of the left hand side? 1 over y times y prime. We are doing implicit differentiation here. Y is a function of x. We are taking the derivative of ln of y with respect to x, not y. So what's the derivative of ln of y with respect to x? It is the same as ln of the derivative of ln of y with respect to y multiplied by the derivative of y with respect to x, which is y prime. So we get 1 over y prime. So what is y prime then? Y prime would be y multiplied with this quantity. And finally, you can plug in what y is. So y was x plus 1 over root of x minus 2. And you get 1 over x plus 1 minus 1 over 2 times x minus 2. You guys agree with that? Everybody's okay? Now, if I ask you a question like this in the exam, you can leave your answer as it is here, but let me show you how to simplify it a little bit further. Basically, you're going to multiply out, okay? If you multiply out, you're going to get 1 over root of x minus 2 minus x plus 1 over 2 times 2 times x minus 2 to the what? 3/2. Very good. That's what you get. And what's the common denominator? It will be 2 times, which one is the bigger power of x minus 2? Bigger power is 3/2, right? So now you divide the common denominator by this guy. What are you going to get? In the numerator, you're going to get 2 terms. The first term, you divide the common denominator by the first denominator. You end up with what? 2 times x minus 2, right? And then when you the second one will be just x plus 1 here, right? You agree? And what is that? 2x minus 4 minus x, so that's x. Minus 4 minus 1 is minus 5. Everybody's okay? Now, I agree with you if you say that if I applied the quotient rule to begin with, I could have done this problem much easier, and I agree with that. But the point of doing log differentiation isn't this problem. I just wanted to show you a simpler example first. But the point of log differentiation will be obvious when you look at my second example. Suppose that you have the function y to be x to the 3/2 root of x squared plus 1 over 3x plus 2 to the 5. So basically, whenever you have a function which has many factors and which has many factors, some of the factors might have negative powers, for example, then you can always apply the log rule to make the function, to break up the function into simpler functions. Okay, so in this case, I'm going to apply the log. So if I apply the ln of y, I am going to get what? Ln of the numerator. When I apply ln on the right hand side, right, I can apply the rule number 1, right? What does it say? I'm going to skip a line here. I'm going to say this is ln of the numerator, right? Ln of the numerator minus the ln of the denominator, right? And what is, I can apply rule number 1 now. Ln of x to the 3/4 plus ln of root x squared plus 1 minus ln of 3x plus 2 to the 5. And then I can apply rule number 3, 3/4 ln of x plus half ln of x squared plus 1 minus 5 ln of 3x plus 2. Okay, so I applied all the log rules and simplify it. Rewrite the function as a sum of simpler functions. And now I'm going to take the derivative of both sides. If I take the derivative of both sides with respect to x, what do I get? On the left hand side, I get 1 over y times y prime. What's the derivative of the first term on the right? Three-fourths 1 over x. What's the derivative of the second term? Okay, you're taking the derivative of ln of x squared plus 1, right? if x squared plus 1 were just x, then the derivative would be 1 over x squared plus 1, right? If it were just x. But it is not, so I have to multiply by the derivative of x squared plus 1, which is 2x, minus 5 times derivative of ln of 3x plus 2. If 3x plus 2 were just x, the derivative would be 1 over 3x plus 2, but it is not x, so you have to multiply by the derivative of 3x plus 2, which is 3. Okay? Again, we are applying the chain rule here, right? So what is that? What I get is y prime then is equal to y multiplied by 3 over 4x plus 1 over 2 times x squared plus 1. Oh, actually, sorry. Let me erase that. It is going to be x divided by x squared plus 1, because 2 cancels out, minus 15 over 3x plus 2. And what's the last step? Plug in y to be whatever y was given, right? What was y given? Y was given to be this quantity here, right? So you plug that in at the end. Clear? Okay, let me know if you're done writing it down.
Once you plug in, you have to multiply it through and simplify it.
Yes. In the exam, you don't have to. In WebAssign, you might have to. I'm gonna let you know. Okay, so you should start doing the homework, but on Thursday I'm going to go over problems similar to the WebAssign, and then I'm going to let you know how much simplification is required. Okay, but at this point, let me just say that you should multiply out and simplify as much as you can. Okay. Everybody's okay? All right. Okay, log differentiation is an important concept that you have to know. Here's I don't want to call it a theorem, but let me call it one. Let's say what I want to do is I want to find the derivative with respect to x of ln of absolute value of x. Okay, so that's what I want to know. What's the derivative of the function ln of absolute value of x? Now, some of you will probably guess that it is 1 over absolute value of x, right? And that's the wrong guess. Now, how would I find this derivative? Those of you who have taken Calc 1 with me, remember what I said. If you see an absolute value function, absolute values are usually annoying. So whenever you deal with them, what do you do first? What's that? Get rid of them. How? Well, ln of absolute value of x. Notice that if x is positive, if x is so, well, first of all, what's the domain of this function, ln of absolute value of x? What's the domain of this function? All reals except
0.
Except 0. Ln of absolute value. Remember, you can apply ln only to positive numbers. But absolute value of x is positive when x is negative. So this ln of absolute x will be defined for any x except for 0, because ln of 0 is undefined. So when x is positive, notice that ln of x and ln of absolute value of x are the same, right? Why? Because if x is already positive, what is absolute value of x? It's the same. Right? If x is 2, what is absolute value of 2? It's 2. Right? However, what if x is negative? It will be ln of negative x. It will be ln of negative x. Why? Because if you know x is negative, then if you multiply x with the negative sign, you get positive of that, right? In other words, if I have x to be, say, negative 2, right, then notice that negative x would be positive 2. So what would be the absolute value of x? Absolute value of x is the same as negative x in this case. So when x is negative, absolute value of x is negative x. So now we take the derivative. First of all, we are going to assume x is positive. If x is positive, then what's the derivative? What's the derivative of ln of absolute value of x? That's the same as the derivative of ln of x, which is 1 over x. Right? Now let x negative. Well, then the derivative with respect to x of ln of absolute x is the derivative with respect to x ln of negative x. Now what's the derivative? I have to apply chain rule now, right? If negative x were just x, then the derivative would be 1 over negative x. If negative x were just x, but it's not. Multiplied by its derivative, negative 1. What do I end up with? 1 over x again. So it doesn't matter whether x is positive or negative, the derivative is 1 over x in both cases. So I could say what? I could say the derivative with respect to x of ln absolute x is 1 over x, and this is as long as x is not 0. Right? So it is, the derivative is not 1 over absolute x, it is just 1 over x. Is everybody clear? You need to remember this derivative, okay? I suggest that you start a notebook or just a sheet of paper where you write down all the formulas, okay? Let me give you a immediate consequence of this. A corollary means immediate consequence of the previous theorem. If I look at the integral of 1 over x dx, what did you say? What's the antiderivative of 1 over x would be ln of absolute x plus c. Okay? Because the derivative of ln absolute x is 1 over x. You guys okay? So here, of course, x is not 0, right? We are going to use this now in a couple of examples. What's the integral from 1 up to e of ln of x over x dx? What is that integral? Say it again. U is 1? Oh, E is the number for which ln of E is 1. The definition of E is that E is a domain value of ln for which ln is 1. Okay? I haven't told you what is the approximate value of E yet. You probably know it from other places, but I'm not going to tell you that, and I hope you don't look it up yet. But at some point I'm going to discuss how you approximate E. And whatever that value is, 2 point something something, that's going to appear at that time. Okay? And I'm going to tell you how your calculator gives you the approximate value of E as well. But at this point, all I want to know is what's the integral here. Okay, so if you look at this integral, you might not have any clue what to do, but you think about what are the techniques of integration I have learned. One of them is U substitution. The other one is integration by parts. So let's try U substitution first. And now if I try U substitution here, obviously you would pick U to be the complicated part, right? Well, the complicated part here is ln of x. So what is du? 1 over x dx. Well, let's proceed here. This integral, I'm going to rewrite that as ln x times 1 over x dx. You agree that that can be done? I haven't done anything. I just rewrote the integrand. The reason is I can now say this is du. This is du. So my integral would be u du. Right? Now, what are the limits of integration? When x is 1, what is u? Look up here. When x is 1, what is u? U is ln of 1, right? ln of 1 is 0. When x is e here again, when x is e, what is ln of e? 1. So the upper limit would be 1. And this would be u squared over 2, 1, 0, and this would be exactly half at the end. Everybody's okay? Are we all okay with that? Okay, let me go down. Let's find the integral. Remember, when we know the integral of sine, we know the integral of cosine. Do I know the integral of cotangent? Do we know that yet? We don't, right? So let's try that. Let's rewrite cotangent as cosine x over sine x. How would you integrate that? You need to observe something here. The derivative of the denominator is what? The derivative of the denominator is sine here, right? The derivative of the denominator is exactly the numerator, right? You know that whenever that happens, you should always do a substitution. Take u to be the denominator. And then what would be du? Cosine x dx. So then, notice that here I am getting cosine x together with dx is what? And sine x is u. So I get 1 over u du. But what's the integral of 1 over u? ln of absolute value of u, right? At the end, and now what is u? U is sine x, and add a c at the end, right? So what's the integral of cotangent? Integral of cotangent is ln of absolute value of sine x plus c. Do you need to remember that? No. You need to remember the integral of sine and cosine and integral of 1 over x. If you know those, you know how to find the integral of cotangent. One exercise for you. Exercise for you is what's the integral of tangent? What is the integral of tangent? Okay, you can do it the same way I did the integral of cotangent. Okay, not quite, because you know when you take the derivative of cosine you get negative sign, and that negative is going to play a role, so you have to work it out.